So in the previous lecture, we have studied about the pulse width modulation and we have seen the important application of the pulse width modulation is that it is used in the industry to uh, deliver the power transfer, to calculate or to deliver the amount of power transferred, which is power transfer to the load, because the PWM signal consists of variable duty cycle pulses, and because of that the amount of power can transfer to the load can be controlled, and it is used in the industry. Now we will continue with the third type of the pulse modulation technique, which is called as pulse position modulation. So in the pulse position modulation is the process in which the position of the carrier pulse train is changed in accordance with instantaneous amplitude of modulating signal, keeping amplitude and width of the carrier pulse train constant. So in the PPM, we are going to change the position, keeping other two characteristics of amplitude and width constant. So if we see the waveforms of PPM, you can see waveforms of PPM are directly not drawn. It is drawn with reference to PWM signal, and this is what principle we are going to use for generation of PPM signal as well. So this is the modulating signal. Then as per the modulating signal, we have drawn PWM pulses when maximum amplitude, that is a maximum amplitude of modulating signal, maximum width of the pulse, minimum amplitude of modulating signal, minimum pulse. Now how we have drawn PPM signal, you project all the trailing edges of the PWM pulses. So when you project the trailing edges of the PWM pulses, you will be drawing a constant amplitude, constant width pulses starting from that trailing edge, starting from that projection. So all the trailing edges you are getting a PPM signal, and once you are drawing with reference to PWM, automatically you will find that position of the pulse is changing because you have drawn with reference to PWM where the width of the pulse is changing. But important to note here, the PPM pulse width of the all pulse is constant, that is tau is constant, only their position is changing. So at all the trailing edges of PWM signal, the PPM pulses has to be drawn. So PPM pulses always comes from the PWM, and that is what we have seen in the PPM generation circuit. So when you have a PWM signal generated from modulating signal and sawtooth signal, which we have seen in earlier lecture, give that signal to the monostable multivibrator. That is, input to the monostable multivibrator will be PWM and output of monostable multivibrator will be PPM signal. Now, what is monostable multivibrator? It is a quasi. Monostable multivibrator is the one has one stable state and one quasi-stable state. Quasi-stable state means once you are giving a PWM signal, as we can see from the waveform, as at every trailing edge, at every trailing edge of the PWM, the monostable multivibrator will get a pulse. And once the monostable multivibrator is getting a pulse, it will trigger and output of monostable multivibrator will go high. It will remain in this particular high state for a certain period of time, which is calculated by RC time constant, and after that time period is over, automatically it will return back to its original position. So monostable multivibrator has one quasi-stable state, and quasi-stable state means it will be triggered, it will go into quasi-stable state and automatically it will return back to original state. So this particular period is decided by the RC time constant of the monostable multivibrator, and triggering of monostable multivibrator will be done by every PWM pulse. And that is why in the waveform we have drawn at every trailing edge of the PWM signal, the triggering is given to monostable multivibrator, and monostable multivibrator will be triggered and it will remain into that quasi-stable state for a certain time decided by RC time constant, and then automatically it will return back to original state. Then again during next cycle, another PWM pulse will give trigger, then automatically it will return back to its original state. So this particular time constant tau is of the monostable multivibrator, which we call it as quasi-stable state. And that is how the PPM signal is generated from PWM signal. So from the diagram, PWM signal will be generated from comparator as we have seen in another lecture, and this PWM signal when given as an input to monostable multivibrator, it will generate a PPM signal. Again, monostable multivibrator is a one which has one stable state and one quasi-stable state. It will go into quasi-stable state once it gets triggered, and it will again return back from quasi-stable state to stable state after the completion of that RC time constant. So here we are giving triggering through PWM pulse at every trailing edge, and the resultant waveform is our PPM waveform. Now we will understand with the help of this diagram that how a PWM signal is detected or demodulated. So here we have some reference point marks, point A, point B, there is point C, point D, point E, and point F. So PWM signal plus noise will be received by a PWM demodulator. Pulse generator will be shaping the pulses so that noise will be overcome from that. Then the pulse generator will be giving the output to ramp and pedestal generator. Also it will give output to reference pulse generator. Now let us look the waveforms at point A so that concept is clear. At point A, you are receiving a PWM signal. So see, this is PWM signal, but the noise contaminated PWM signal. So you can see there is a noise present into that. Then that signal is given to pulse generator. So pulse generator will give proper shaping and you will get a proper shaped output, which is called as regenerated pulse waveform. That is at point B. So at point B, you are getting regenerated pulse input. Now, the reference pulse generator is generating the waveform of point D. So you can see at point D, it is generating a reference pulses at every starting edge of the PWM signal. So you can see in between the pulses are generated and every starting edge, the reference pulse generator is going to generate a pulse. Now another generator which is present here, which is called as ramp and pedestal generator. So ramp and pedestal generator is going to be triggered at the PWM signal starting. So you can see at every starting edge of the PWM signal, the ramp waveform will start generating the ramp, then it will be constant. So once the PWM signal is over, it will maintain its constant. When another PWM pulse come, again it starts rising, again it will maintain constant. When another PWM signal comes, again it will rise. So this rising time period is dependent on the width of the PWM pulse, and that is why you will be able to see this kind of waveform. So during this particular period of PWM, the ramp wave is rising. So here you can see pulse width is narrow. So rising is only till this much period. Here the pulse width is wide. So rising is for the more period. Here the pulse is narrow. So rising is for the less period. And you get this particular waveform at point C. So point C is here. This is point C. Now what happens? Waveforms of point C, that is our ramp wave, and the reference wave, they both are added, and that is the waveform at point E. So at point E, you can see this is the addition of waveform C and waveform D. So above this waveform D will be going above point C, and you will be getting like this waveform. Once you are getting this particular waveform, the next point is given to a clipper. These waveforms are given to a clipper. Clipper will have some predetermined level, after which the signal will be clipped. And you can see the output of the clipper is point F. So you can see at point F, you are getting a pulses which are having amplitude change. So this is the clipping level. And beyond this, all the signal is clipped, and only you will be getting these pulses at the output, wherein you can see this is our PAM signal. So what is the principle of PWM detection? Similar to that of FM. What we have done in FM? We have converted FM to AM, and then AM signal will be detected by a low pass filter and a diode detector. Similar to that, in PWM also, PWM signal is converted to PAM signal with the help of this particular block diagram, and then PAM signal will be detected by a low pass filter, like how we have seen a PWM demodulator signal. So this is what is the detected output which we get here is our original information signal. So what is the process? Convert PWM signal to PAM signal and then detect PAM signal with the help of low pass filter. And waveform at all the points are drawn in this particular slide. So ramp wave will be generating the rising pulses till the width of the pulse, and then both the pulses are added and then it is clipped. So you get a PAM signal which can be demodulated by using low pass filter. So this is the PWM detection. Now for the PPM detection, again the same process will be done. Only in the PPM detection, what we will do, we will convert PPM signal to PWM signal. Then PWM signal will be converted to PAM signal, and then PAM signal will be detected by low pass filter. So PPM pulses, noise contaminated PPM pulses are given to pulse generator, which is given to reset terminal of this SR flip flop, and the reference pulse generator are given to a set terminal of the SR flip flop. The output of SR flip flop will be a PWM signal. And once you get PWM signal at the output, you use PWM detector, which we have seen in the previous slide. Use PWM detector, convert PWM signal to PAM signal, and then detect the PAM signal with the help of low pass filter. So the steps remain same. Convert PPM signal to PWM, then detect PWM signal by PWM demodulator, that is PWM to PAM, and then detect PAM with the help of low pass filter. And for the PWM demodulator, this is the circuit, this is the waveforms, and for PPM, we are converting PPM to PWM with the help of SR flip-flop, and this is the comparison between PWM, PAM, PPM. The waveforms are important, definition is important, and what is the bandwidth requirement. The very important advantage which we get in PWM is the noise and interference is minimum in PWM and PPM. One more point, PWM signal is also called as pulse duration modulation because duration of the pulse is changing, so it is called as PWM or PDM.